Alrighty, folks, here is 36 through 40. Whenever we have doubling or things in half-life, the formula that comes to mind is, okay, well, I'm going to start out with some original amount, and then that original amount is either going to get cut in half or double. In this case, it's doubling so many times over some period. So in this case, we start out with 700 amoebas, and they're going to double every 26 minutes, and they want us to find out how much time before we get to a billion amoeba. So for this guy, you throw it into your solver and then you find your time. This answer though will be in minutes, and they want the answer in hours, so don't forget to divide by 60. All right, 36. How long does it take to pump 1.5 acre feet using a pump that delivers 850 gallons per minute? So the idea here is, if we take that volume and if we divide it by the how quickly the pump moves that water, that's going to give us the time. But we got to get the volume. That's 1.5 acre feet. And we need some conversions between acres and feet. So we need to remember that there are 640 acres in a square mile, and a mile is going to be 5280. So we start with a 1.5 acre feet, and we're going to do some conversions to convert that to cubic feet. We convert the acres to square feet using the 5280 squared conversion. And that's how many cubic, and then we go from there to cubic inches, because our pump is moving 850 gallons per minute. Now, if you don't know how many cubic feet in a gallon, that's understandable, but we are expected to know in this contest that there are 231 cubic inches in a gallon. So we use that conversion factor for the 850 gallons per minute. And so this is how many cubic inches we're moving every minute in our pump. And then from there, we divide the two quantities to get the minutes, and then divide by 60 to get the hours. Okay, let's go ahead and take a look at 38. Tokyo, Japan, and Tehran, Iran lie on a latitude of 38.73 degrees. Those 47 minutes, those are arc minutes, and you need 60 of those to make a degree. So we take 47, divide by 60, and we get 0.783 repeating. We're going to do the same thing with the other arc minute measurements, the 2 arc minutes and the 5. We divide them by 60 and add them to the original degrees. Okay, so how do we solve this problem 38? 38 can be a little intimidating and challenging because, like, whoa, there's a lot going on here in 3D. Well, the good thing is that at the end of the day, we're going to try to do it as a 2D problem with an arc. So from Iran to Japan, there are so many angles or degrees between the two cities. And when we get that angular separation, that's going to be the number that we're going to plug in here for the arc length formula. Arc length says that the distance of an arc is going to be the radius of that arc times the angular separation between those two subtended points. Now, the challenge is that in this case, even though they give us the angles between Iran and Japan, they don't lie on the equator. They actually happen to lie on some angle of latitude, which is going to change the radius of the arc that we are working with. It's no longer the radius of the Earth. Now, if we look at our trigonometry here, this right here is the radius of the Earth, and this is going to be the angle of latitude. Now, if we drop down a perpendicular, here we can see that we get a right triangle. And so it turns out that the radius at latitude is going to be the radius of the Earth times cosine of that latitude angle. So putting it together with the arc length formula, all of this becomes the radius of the Earth times cosine of latitude. All of that is the radius of the little circle at that latitude. And then the angle between the cities is going to, you take their two coordinates and you subtract them. Now, if one was on the east of the prime meridian and the other one was west of the prime meridian, we would need to actually add the angles. So here the angular displacement is theta minus theta, and you would need to remember that if one is west, that is technically considered a negative angle. Anyways, you put that all together, the 141 minus 52 degrees. The challenge is that that needs to be in radians. I forgot to mention that earlier. So you convert that to radians, 1.55 radians. You multiply that by cosine of the latitude, which is 38.783 repeating. You multiply by the radius of the Earth, and there you go. All right, let's go ahead and take a look at number 39. 39 is recognizably a CASP problem, area over semi-perimeter. So how are we going to get the area, and how are we going to get the semi-perimeter? Well, I think the easiest way to get the area of this triangle, based off of what they give us, is they gave us the base and an angle here. We've been seeing that on this test, there's a lot of like split the triangle up in two and then use tangent to get the height of those triangles. And that's what we're going to do over here. So recognizing that if we cut that triangle in half, it's going to have a height or an opposite side of that angle of 41.1. And to find the adjacent, we would need to use tangent. Rearranging the tangent expression, we get that the adjacent is 41.1 over tangent of 18.5. While we're here, we can also rearrange the expression to find the hypotenuse, because we're going to need that for the semi-perimeter. So when you rearrange the sine expression, you divide it over and you get 129.5 for that side length. Putting this all together for the radius, the area is going to be base times height divided by 2, and then the semi-perimeter is going to be the three sides added up. So area is base times height. There's technically a 1/2, but for the semi-perimeter, there's also a 1/2 that is going to cancel, and that's what I had over here. Okay. Number 40. On number 40, we can see that they want us to find this side over here. They gave us that angle right here, so we can get its supplement by taking pi away from that in radians, 1.74. Now, once we know that angle, if we're able to find this side length right here, we can go ahead and do law of cosines, and that's what we're going to end up doing. Now, how do we do that? Well, they gave us the height and the angle, so if we use sine, we can find out the side length that I was talking about right now, which is going to be here in orange. Okay? So we're working with this right triangle. The 57.9 divided by sine of 1.4 is going to give us this side length right here. Then from there, we throw it into law of cosines and solve for it.